Well, I want to thank you all for having me back again. I really appreciate the opportunity. I know this talk on Einstein's theory of relativity is going to be quite a bit different from some previous talks where you're looking at things more observationally, filters, telescopes, and things like that. So my background has been more in the theoretical side of things, more in quantum mechanics and relativity. But over the last 25 years, I've gotten very much interested in observational astronomy. But for me, this is my first love. And it connects back to the things that our membership does. You know, a lot of Einstein's predictions allow us to better understand the universe and go out and explore and look at things. There's a lot of material to cover today. And, you know, this is non-mathematical. So it's to explain things and give you some examples to prove that it does work. And we'll go from there. Anyways, I'm going to focus primarily on general relativity, not special relativity, the other half of it. I'm going to talk about it real quick, but it's the general part that deals with gravity, that deals with, you know, all kinds of things that we take for granted nowadays, like the topics of gravitational waves and gravitational lensing and things like that. So, and I am learning Russian, so I like to throw that into my titles and places wherever I can. Okay, so tonight's agenda, it's like I said, it's going to be fast moving, and I'm happy to answer questions right afterwards and if critical during the talk. And certainly anytime you want to email me, or we can even have a chat. So we're going to cover basic classical view, a bit about Albert Einstein. We're going to talk about the two subsets of relativity, and then go right into the big chunks of predictions and examples, and at the end, finish up with controversies and move out from there. So, as we probably all of us know, physics is the science of matter and energy and how they interact with each other. And this science goes back, it's probably one of the oldest, since astronomy is one of the oldest, and astronomy is a subset of physics. It goes back to 3500 BC or so, and is deeply reliant on mathematics. In fact, at times, certain aspects of mathematics was invented simply so we could work with a better understanding of our universe and explain it. It covers a lot of subtopics. You know, as you can see here, astrophysics, classical dynamics, E&M, all the way into chemistry and other fields. But our focus, again, is going to be on relativity. And despite the fact that it's highly and deeply embedded with math, that's not what we're going to get into here. That's not what this is about. But I do say it to emphasize it. And that doesn't mean that it's any worse than other subject matter. It's just a language that takes time to learn. And I believe anyone can do that. So first, a little bit about classical theory. It studies, again, the motions, classical relativity, motion of things and how they relate to each other relative to different observers. Isaac Newton is preeminently associated with classical mechanics, which is also known as Newtonian mechanics. And in his worldview, or the view of the universe, everything is falling, right? If you shoot, you know, if you toss a ball, it falls to the ground. If you can shoot out a cannon further, it'll go further and then fall to the ground. But if you can shoot something fast enough, hard enough, it'll go around the Earth because orbits are falling. Items are falling and they just continually orbit. And from that he revealed, and from other things, he revealed that his key equations are force is equal to mass times acceleration, a very key and fundamental equation of physics. And of course, the force of gravity, which I'm sure many of us have seen. G is the universal gravitation constant. You have the two masses like the moon and the earth, and the distance between the two masses. And that'll allow you to understand what is the strength of that force of gravity. That's key to understanding this, the force. And with that, he rigorously described things in the universe. And he even invented calculus to better explain those things. It's those equations that led to many others that allowed us to go to the moon, allow us to put satellites into orbit, and send probes into deep space. But how does it view the mechanics and classical mechanics view relativity in its classical view? So let me give you an example. That's the best way to understand it. If you have this truck driving along on the freeway, and let's say it's moving at 60 miles an hour, all right? Trust me, this won't be that boring. On the truck, you've got Alice and Carol, and basically, Alice tosses a ball to Carol at 20 miles an hour. Simple enough. Now, to her, Alice says, hey, the ball traveled at 20 miles an hour, and Carol says, ditto, of course. Even though they're on a truck bed moving at 60, the ball to them is moving at 20 miles an hour. Now, they pass Bob at the time when they're tossing, when the ball is tossed, and from Bob's perspective, relatively speaking, the ball traveled at 80 miles an hour. It makes sense. That's how things work in our everyday world. So that's classical relativity. And you're wondering, well, what the heck is the relativity part? It is additive. That for Bob, it's 60 plus the 20. For Alice and Carol, it's just the 20. That's something we're familiar with. And that's the relativity part of it. How is it viewed by both of them? So, and that's been around for a long time, and it makes great sense. However, there are limits to how well this works. It works for slow-moving objects, slow-moving things. At higher speeds, this Newtonian physics, this classical theory begins to fall apart, and falls apart miserably. And so what I mean by slow things that are about 10% or less than the speed of light. Well, that's still about 18,600 miles per second. We've got nothing that travels that fast. The Parker Space Telescope goes, I think, several dozen miles per second. So and that's our fastest thing. Voyager's moving at 38,000 some odd miles per hour, or kilometers per hour. So you can still move pretty fast, but it's designed for slow moving, below the speed of light at around the 10%. But a lot of things move much faster, right? Obviously light and things like that. So this failure required a new approach. In other words, what classical mechanics predicts and how it works doesn't apply to a lot of things that are moving very fast. And that means the theory has failed, and that has to be augmented or replaced completely. It has to agree with observations and be able to make predictions. Otherwise, a theory is no good, and it doesn't work the other way. If you do an experiment correctly and the outcome doesn't agree with theory, then you have to go back and look at the theory and what's going on. Well, along comes Albert Einstein, and Einstein had a whole different take on everything. But first of all, he had an interesting life. He was born in Germany in 1879, and literally, he was considered to be a slow guy mentally. He had academic failures. He was considered lazy, all of these things. And he finally got married in 1903. And by that time, when he did graduate, nobody wanted to hire him. So he basically got a job as a third-level patent clerk in the Swiss patent office. And around 1905, while working there, he finally got his act together and had his miracle year, and continued to progress. And because of that miracle year, he ended up with a professorship. And in 1915, he had an even more profound year. He was also tired, and he ended up getting divorced. But based on some of his work, he got the 1921 Nobel Prize and was a main person at the Solvay Conference in 1927. Came to the US, went to Roosevelt, signed a letter among other scientists saying that Nazi Germany was going to be working on an atomic bomb, and encouraged that. And his later years discouraged the use of atomic weapons, and passed on in 1955. But this was a brilliant man. Going back to 1905, which was his annus mirabilis, Latin for his miracle year. And in that year, he published several papers. One is the photoelectric effect in March, which dealt with quantum mechanics, which he was not a big proponent of, but eventually led to the development of quantum mechanics, and which talked about a wave-particle duality. Brownian motion, which allowed us to better understand atoms and molecules. The Special Theory of Relativity in June, which I'll talk about in a bit. And mass energy equivalence in September, a paper he wrote in 6 weeks that deals with the energy content of matter. So, by the way, he did all of this while working as a full-time patent clerk. What's amazing about this is, I can tell you right now, any one of these 4 works would have made him basically a hero of the Republic, a name to go down in history and science. But he did all 4 of these and so much more. Amazing amount of work that he had done. But I do want to mention here real quickly his mass energy relation. And as we know him, most people will say, hey, E equals mc squared. That's what I know about Albert Einstein. And this was an add-on to his theory of special relativity. And this process that converts matter into energy, it applies in a very special case where the mass is not moving, and that's critical, but it generates an enormous amount of energy. Now, mind you, you might say, well, riddle me this. What happens when I burn wood? That's a chemical reaction. That's not conversion of matter into energy, where the matter completely disappears. In a chemical reaction, if you look at it, the mass on one side before and the mass after is the same, and the energy comes from breaking of bonds. So things like that. And, you know, when you say the internal combustion in a gas engine is 25% efficient, wow, that's amazing. Well, those are all chemical bonds related. This is different. But if you could take a gram of mass and convert it to pure energy, it would generate 24.9 megawatt hours, which converted would be about 1.4 times the yield of the first nuclear bomb we blew up, which was the equivalent of 15,000 tons of TNT. So there's a tremendous amount of energy involved here that he had developed. And this work was in this paper, and basically it was based on the equations of James Clerk Maxwell and Heinrich Hertz. And ultimately, the result of that quick work that he did showed that here, that if a body gives off the energy L instead of E here, the form of the radiation, its masses diminishes. This is simply E equals mc squared. So there you have the E equals mc squared. I'm going to move on from here. Theory of relativity. Okay, so let's talk about that. Now let's get into the meat of things. It's all about things that are moving and interacting. That's what physics is, right? And relativity studies how motion is experienced from different perspectives. That's what relativity is about, relative motion and things like that. It describes the behavior of things moving at near or near the speed of light. It also talks about, we'll learn when we get into general relativity, things that are heavy bodies, such as a planet or a star or a moon and things like that. This was developed in the early 1900s by Einstein and is the foundation, a foundation of modern physics. In the 20th century, there are 2 pillars of physics that govern everything and kind of, in my opinion, overshadow so much, and that's relativity and quantum mechanics. And the 2 have done brilliantly at being able to explain our universe and help us usher in the modern era. And I'll explain all those with examples, why I feel it's the way it is. And again, it's a foundation of modern physics here. So it is mathematically complex, it is non-intuitive, but it is exceedingly accurate for the last 100 years. It accurately describes known observations, which is what a theory has to do, right? Previous experiments. It predicts things that have been proven to be highly accurate. And that's exactly what a theory needs to be able to do. It's comprised of two subtheories: special relativity, which applies to things moving at a constant speed at or near the speed of light. When things move in one direction at a constant speed, they call that an inertial frame of reference. That's all it means. The first time I heard that, I went nuts trying to figure out what that meant. It just means it's moving at a constant speed in one direction. The theory of general relativity, the other half, which is a generalized version, meaning special theory is a subset of it, includes non-inertial frames, meaning things that accelerate, decelerate, go around things in a curve, move not in a straight line. So it's much more complex. And it is also, general relativity is a comprehensive theory of phenomenon of gravity as a phenomenon of space-time curvature. And so that, the first time I heard, I was trying to figure out what the heck is space-time curvature? Well, space-time is a model that unites space, three-dimension space that we know, X, Y, and Z coordinates. I think we're all familiar with that. Straight, back, left, right, up, down, with time. Okay. It was actually first proposed by a guy named Minkowski in 1908. He was a mathematician who wanted to express some of Newton's work in a different formulation. So a crude example might be, for example, is if you want to meet someone, you have to agree on a location, an exact location, at an exact time. If you show up at the correct location at the wrong time, well, you're in the wrong space-time location. So space-time, they work with each other, space and time. Now, it's not that simple, I realize that, but I wanted to be able to explain that in a way that, you know, it's not as complicated as it seems. Special relativity can be derived and explained with high school algebra. Not the case for general relativity. So let's talk a little bit more deeply about special relativity here. And, you know, I know, Raj, you're working on making sure that things, the chat is managed, so I'm not going to be looking at any of that. But if somebody comes up with a thought that is just going over their head, especially, please let me know. So,
will do.
All right, sir. Thank you. Now, with special relativity, it was part of that miracle year of his, right? It completed in early 1905, titled On the Electrodynamics of Moving Bodies. You know, back then they also had great titles for articles. Published June 30th, 1905. It predicts the behavior of moving objects at high speeds where classical equations fail, okay? So that's a significant fraction of the speed of light, c, which, by the way, some have said c stands for constant, or it came out of Maxwell. He used it first and Einstein used it. Others have said it means celeritas. The c comes from there, which is Latin for swiftness or speed. But I love understanding, why would you call it c? Why do you call the gravitation constant g and these other things? So in case you're interested, I believe that's why they call it c. It involves constant speed. No, it's an inertial frame. Fair enough. Two postulates come out of, we're just summarizing here for special relativity, but I could talk about special relativity through a 12-hour class, and it would be a lot of fun. And you just you need a ruler, you need graph paper, and a few algebraic equations. But the two postulates out of special relativity are the laws of physics are the same in all inertial frames, rest or moving at a constant velocity. In other words, if you are, no matter how you look at it, everything behaves the same. Nothing changes. It's not a matter of perspective. The laws of physics are the same, which can make sense. It can also be applied back to lower speed relativity. But The speed of light, the other outcome in a vacuum, has the same definite value c in every inertial frame. Huh? So what does that mean? It means basically that regardless of how fast the source and observer are moving relative to each other, it's always c. It's not 2c, like, throw the ball and it's going to be 60 miles an hour plus 20 miles an hour gives you 80 miles an hour. It's always going to be c. For example, if the speed of light was 65 miles an hour, then on that truck that's moving at 60, she throws the ball at 20, you couldn't say it was 80 miles an hour. The most it can be is c. It contradicts the first one. It seems to contradict, but it makes sense, and I'll explain that in a second why. Let me give you a little more detail. The same laws of physics in all inertial frames. If you drop a pen in a moving car at a constant speed down the freeway, the pen drops. On an airplane, if you stand up and you drop the pen, it still drops. On a train, the same thing. They all behave the same way, unless it's accelerating, but this is not the case, right? As I said, it's an inertial frame, therefore it's not non-accelerating. And by the way, if you couldn't feel the vibration of the car or the plane or the train or hear the sounds or feel any bumps or any of that good stuff, you would never know. There is no experiment to tell you you're moving. All you know is that you're inside something, you drop something from all perspectives, it all looks the same, and there's no way for you to tell that you're moving at that point. You can only tell if you're moving relative to something else. Oh, I see the hills go by. I see the ground beneath me go by. I see the mountains as the train goes by, and things like that. The speed of light is the same for all observers in every reference frame. This one's a little harder to explain, so instead of talking about it, let me show you what I mean by it. And you have to kind of accept it. It's counterintuitive. You got Bob and Alice, right? Bob is standing still there in his spacesuit in space. And here comes Alice traveling at 80% the speed of light towards Bob. Now she's going to come up on him and fire a laser beam. Boom. Alice just fires a short laser beam. Now Alice is going to see that laser beam go away at the speed of light from her, even though she's moving at 0.8 c herself. But Bob, on the other hand, isn't going to see 1.8 c, her speed plus light. He's only going to see c. How can that be? Okay, he cannot see it any faster. The speed of light is a constant, cannot be observed as being any faster than that. Now, before anyone asks, well, I heard that the stars and galaxies are moving away from us at faster than the speed of light. I am talking about how things move in space. I'm not talking about the expansion of space itself, which is a different matter. Okay, we're not going to get into that, but those are two different things. So what you have to bear in mind, a very big outcome is going to come out of all this. If distance is equal to speed times time, right? If I'm traveling at 60 miles an hour, that's my speed. I do it for 1 hour, my distance is 60 miles. Or for 2 hours, it's 120 miles. But in this case, no matter what you do, the speed is always going to be c, because it is a light, and it's always going to move at c in a vacuum at that speed. So you have to understand one of the outcomes, or the major outcome, is that things like distance and time are no longer fixed. They're malleable, and that is not intuitive at all, okay? Time especially. So there are some incredible consequences as a result of this. In summary, the laws of physics are the same in all inertial frames of reference, right? Now, and when we get to the examples, this will make a little more sense. Not as to why it happens, but you accept the fact that it happens, and you'll see how it's such a powerful tool. Everything is moving relative to each other. These things, these effects that I just talked about are insignificant at low speed, below the 10% the speed of light. And also the speed of light is a constant in all inertial frames. It is a cosmic speed limit. There's no way around it as far as we know. We're not talking about wormholes and all that. Those are all mathematical, theoretical. Nothing has been observed, and nothing has allowed us to move at the speed of light. We can talk about black holes and what happens in the singularity. We know nothing about what happens in the singularity. We can talk about it. We can make YouTube videos about it all we want. We know nothing what happens. We know nothing about what happens in the middle of in the center of a black hole. And so nothing that has mass can travel at the speed of light. Well, what do you mean by that? Well, remember what I said a little bit ago, E equals mc squared. The reason I focused on that is, think about it. Energy equals mass times the speed of light squared. Energy equals mass times this number, the speed of light squared, right? But energy equals mass. Energy is proportional to mass if you get rid of C. So if I add more mass, I get more energy. If I throw more energy into it, it's going to get heavier. If it gets heavier, I have to throw more energy to get it to go faster, but it'll get even more heavy. It's not a crude, but a one way to look at that and try to understand a little better. So if anything has a mass, it can never reach the speed of light. By the way, if it's massless, it can only travel at the speed of light, like photons, like gravity waves and things like that, gravitational waves. So this is all counterintuitive, but it is real. Key takeaways. This is the part that matters. I mentioned in time, and it can be malleable. That's known as time dilation. And there's a great thought experiment called the twin paradox, where if one twin takes off at 90% the speed of light for 5 years and comes back, the older twin is whatever, 25 years older than the one who just came back. That's nice, but that's not the paradox, by the way. That's easy math. The paradox is that they should both see the other one getting older, not themselves. And there's a way to explain that. That's the paradox. There's something called muon decay. This is real, not a thought experiment. So particles from the sun that are emanated, they can come into the Earth's atmosphere, react with oxygen, and they're moving at like 60, 70% speed of light. As it turns out, they should not be able to reach the surface of the Earth. Maybe, let's say, whatever the experiment says, only 2 or 3 should reach the Earth. Instead, they've detected 60, 70, 80, 90,000 of these particles. And the only way that makes sense is because of time dilation or length contraction. And when you run the calculations, it looks like muon decay makes sense. It shouldn't reach the Earth, but it does because time is shortened or distance is shortened. Therefore, the distance it has to travel is much less. And it's a really cool explanation. I've got a whole set of slides in those, but it does explain that. Length contraction. Yes, there's a experiment. You can do a thought experiment on how do you get a 10-foot, let's say a 20-foot pole into a 10-foot barn. You can do the calculations and I'll show it as well. And things do get longer and things do get shorter as they start to accelerate closer to the speed of light that's been measured. Mass expansion. You can take an electron and accelerate it in a particle accelerator, and they've been able to, as they get closer to the speed of light in its acceleration, its mass increases by 60,000. So, and then you add more energy, then it gets heavier. Then you need more energy to make it go faster, it gets heavier because energy and mass are equivalent. That is the big takeaway here. How much does time, length, and mass get affected is known as what's called Lorentz factor. It basically says this: gamma is this equation. And you can see that if you move at 60 miles an hour, if your velocity is 60 divided by the speed of light is really tiny, squared is even tinier. 1 minus a really tiny number is 1. Square root of 1 is 1. Gamma is 1. Okay, that makes sense. Therefore, things that deal with Newtonian mechanics, moving it below the 10% speed of light, these relativistic effects really aren't there. So not going to matter. So we can go about our world by using equations like distance is equal to speed times time, instead of distance is equal to t0 over the square root of t1 minus t0, v over c squared and all that, making into a complex equation. These equations at low speed just pop out the usual equations we're used to, that you can then do basic calculations with. If you are approaching the speed of light, then gamma becomes bigger and bigger and bigger. And as you get closer and closer, you can see when you're about 10%, it's still 1, nothing happens. But you start getting faster, it gets a bigger and bigger factor. In other words, here, if I'm just traveling at 10% the speed of light, you go to the moon and back at the speed of light, no big deal. But if you're traveling at, 0.999 the speed of light, well, let's say that number happens to be 15, and you travel that way for a year, I'm going to be 15 times 1 year longer, older than you when you come back. So that's sort of the correction factor. But don't worry about the math here. What matters here is that time is malleable, length and mass are all malleable. There's length contraction, mass expansion, time dilation. And it's pretty powerful stuff, but it's real. It absolutely is real. Okay, so let's talk about general relativity now, and then I'll tie it all back together. I know that we have a limited amount of time, and I pressed the wrong button. So let's just go through this real quick. Sorry about that. All right, general relativity. So Einstein afterward began to focus on a generalized version of relativity, not just this moving at a constant speed, because in the real universe, things move at not constant speeds, and they don't move in a straight line. So this also included a comprehensive accounting for gravity as well. Isaac Newton described the effects of gravity, but he never could propose the mechanism. He even wrote, I leave that for future generations or others to figure that out. But he did see it as an attractive force. The apple falls from the tree to the ground. Well, in 1907, Einstein pondered how a person in free fall would not feel their own weight. So he was thinking about that, and anecdotally, he was watching a window washer. And so it's an anecdote, who knows? As we probably learned, an apple really didn't fall from the tree that gave Newton his eureka moment, but this is sort of like that. Who knows if it really happened, but according to Einstein, are people that say he was watching a window washer on a tall building across the street. And he wondered if that guy fell and before he died, for a moment there, he would be weightless, is what he would feel. And there wouldn't be any gravity. There would be none of those things. And that elimination of gravity laid the foundation for his general theory of relativity. Potentially watching a guy die changed the course of science for humanity. And it allowed him to reduce the complexity of his work. Bear with me, we're getting there. Over the next 8 years, this led to a brand new description of gravity. And He absolutely didn't consider gravity as a force as Newton did. Gravity is not a force. It's not some attractive force and things like that. Now, you might say, well, Mishra, I heard about this particle called the graviton, which causes, if they discover it, it attracts a force and all that. Yeah, well, that's quantum mechanics. And that's a different beast right now. But Newton felt it was a force. Einstein did not consider it to be a force. By 1915, he theorized that massive objects cause a distortion in space-time, which is felt as gravity. What the heck does that mean? And by the way, that whole thing about the guy falling, the window washer, years later, he did recall that free fall idea was one of the happiest thoughts of his entire life. He has been known to have said that. So curvature in space-time is perceived as the force of gravity. Okay, this is critical. And there's a little glitch there, but the word time shouldn't be there at the end. So you can see in this one GIF, as it isn't an attractive force, but it causes a curvature in space-time that causes the planet to orbit or a moon to orbit a planet and so on. Gravity is warped space and time, warped space-time. This is the more comprehensive theory, and it applies to stationary, that is invariant masses, inertial, those moving at a constant speed, and non-inertial frames of reference, things that are accelerating, decelerating, and so on. It applies to all cases. So it's a very powerful tool. In 3 dimensions, it looks more like this, and even that's not a great way to view it, but it brings it closer to how things look. So gravity in action. I think you've all seen this type of thing before. So the teacher throws onto this trampoline. There's say the sun. And then he throws all these out there, these little ball bearings or marbles, which act as planets, and they go all around. And eventually, there's no magnet-like attraction. They begin to orbit, and obviously they don't because of friction and air and all of that. But the point is made. By the way, there's another point made here that you may want to focus on. When the solar system formed, stuff goes all over the map. It's rotating around all over the place, and they collide with each other. And then whatever's left over is moving in the same direction. Hence, we don't have a bunch of garbage running around, hitting each other, moving in opposite directions. We orbit in the same direction around the sun because all the other stuff is kind of, cleared the path out of the way and coalesced into planets, into moons, and into the asteroid belt, things like that. But it's a wonderful example. It's not a force. That's how that works. So, in general relativity, this is the big equation. It's a beautiful equation. It is ugly. It will make you throw up when you have to go and study it. Here's a book. It's called Gravitation. I use this. It's about 1,280 pages long. So leading to understanding that equation. I don't understand the equation. I've done many problems out of this book, and but it is an amazing piece of work called Gravitation by Kip Thorne and others. And Kip Thorne, some of you may know the name. He got the Nobel Prize for gravitational waves. Plus, he was the lead science advisor for the movie Interstellar at Caltech. So this is what it means. Okay. So look, it's ugly, but here's what it boils down to. This component here deals with the volume of space-time curvature, the amount. This deals with the forces experienced on objects within space-time. This is part of the cosmological constant, which Einstein didn't assume that the universe was expanding. He was trying to hold it together. even though the universe was expanding. And he considered that to be a major failure, the addition of the lambda function here. But it turns out it's actually a good thing. This part here deals with basically the force, the strength, and all that of space-time. This side here is simply dealing with energy and mass matrix. This is just a number. All right, great. That still doesn't make sense. And it can get uglier in the sense that you can break this equation into 10 more, what are called the field equations, and get out of it. But here's what it translates to. On the left side, space-time curvature, all this is proportional to the density, mass energy density. Now, it's still not making great sense, but you bear with me. And by the way, you can change this proportionality to an equal sign by adding this number, 8 pi universal gravitation constant, speed of light to the 4th power. That's just a number. By adding that number, this becomes an equivalency. So, or an equality, not equivalency. So that's what that equation means. Translated, in empty space, the mass energy density is 0, approaching 0. Curvature is flat. Space is not curved, right? If there's no moon or sun, it's just empty space. Things are moving along just fine. You're moving in a straight line. As the density increases, so does the curvature. Make sense? It should. But let me give you a little better example, because this outcome is incredibly cool. So look at it, you know, the universe is 4 dimensions for us, right? Space, time. But let's just look at this 2D thing. If you're cooking along, nobody's in your way, you just move in a straight line. Life is good, air is free. Okay, but there you go. You approach a space-time curvature, a region, because of a large mass, then you start getting curved. Your path is no longer straight. If you're close enough to it, you can get trapped and go into orbit. That's what it's saying, is that the amount of curvature is proportional, is dictated by the amount of matter, mass, and energy. Mass and energy are the same thing, except for this c squared. So they dictate how much things get curved. That's the crux of general relativity. Okay, it's very interesting, but that allows him to explain so much. Okay, so in summary, gravity is not a force that pulls you in. It is the curvature of space-time that deflects the path of other objects. When you fall off a ladder and just a couple of steps, you come back and say, man, gravity is a real beat. But you don't say, because it's easier to say that, oh my God, I slipped and I went down the space-time curvature well of the Earth. Yeah, you lost people as soon as you said I slipped. So you just say gravity. Makes sense, it works. Curvature creates what we call gravity. Massive objects tend to fall towards more massive objects, right? The curvature is created, is caused by light, and by lighter objects is much smaller, fair enough. And just like the moon is kept into orbit around the Earth is much more massive, but the moon does have an impact on our tides. So it does do a lot of things. And it also checks off the boxes. It's consistent with special relativity, which is a subset of general relativity. General relativity also explains the phenomenon of classical mechanics. If you take that Lorentz factor, go down low enough speed, a bunch of terms drop out, and you get the older equations that we've always used. And so that works. In other words, the theory is consistent with what we already have. And it also helps us to understand that space is not separate from time. It includes space-time. Space-time tells matter how to move, and matter tells how to curve, right? Matter is mass. The more mass you have, it'll tell you how much to curve. Space-time is what allows matter to exist and move within it. So it's a very powerful set of conclusions, and it's a very powerful theory, and it has its own predictions. Okay, so far it looks, hopefully I haven't lost anybody, but let me show you some examples, and now you get a much better feel for it. So everything that I've said, the calculations can be done to 8 decimal places to explain our universe around us, which is pretty amazing. And
before we go on,
yes.
Real quick, we have a question from Jerry.
Yes.
What is a tensor?
Tensor is like, it's not a, don't think of it as a matrix. Tensor is a set of vectors. You have scalars and you have vectors, and it's a set of vectors throughout space that allow you to understand all the different forces and motions and things that may be occurring for whatever it is you're trying to study. Okay, so you have a tensor of the first order, of the second order, and so on. You know what? I'll give them a better definition. I just can't think of the best one right off the top of my head, but I will give him a better definition and a nice, easy to understand definition. Any other question you have right now?
That's it for the chat room right now.
Okay, so let's look at the real some examples. I think we've all heard about the precession of Mercury. As it turns out, as Mercury goes around the sun, it's tidally locked to the sun, and Mercury's orbit slowly precesses around the sun. All right, observed. In other words, as it goes around like a spirograph, it moves. And this movement away each time is exaggerated here, but it's 5,600 arc seconds per century. There's 3,600 arc seconds in a degree, 360 degrees in a circle. So it's a really small amount per 100 years. Newtonian mechanics predicts this pretty well, all down to just 43 arc second difference. They couldn't explain that 43 arc seconds. They attributed it to asteroids, to dust, or a 9th planet called Vulcan over 100 years ago. So they didn't steal it from Star Trek. With no changes in Mercury's orbit, that's the symbol for Mercury, General Relativity explained the variance. So this is a test, right? It's old information. GR, can you do it? Actual is 5,600 arc seconds per century precession. Newton says 5,557. The variance is 43. But of that 43, General Relativity picked up 42.98 of it. In other words, it was off by 0.02, which is well within experimental error. So the theory holds. The theory predicted it very well. As Mercury moves towards its perihelion closer to the sun, it moves deeper into the sun's gravity well, which then causes it to accelerate and advance closer. And that ultimately causes the slight variance and causes the precession. GR just passed that test easily. And that occurred, what? I forget, maybe 1915 or 16. He actually did it just to show that his theory was good. It also does the same thing for Venus, which is 8.6 arc seconds per century. Amazing. Theory works. Flying clocks. Well, I'm going to go through this one fast. Basically, in 1971, they flew 4 atomic clocks in 2 different directions for a couple of days, refueled them in air, or they came down to refueled. And then they went around the Earth, and then they looked at the clocks. These are atomic clocks. Macroscopic clock, compared it to US Naval Observatory. Einstein predicted that they should vary within General Relativity, 40 nanoseconds plus or minus 23. So this is within actual measure. Not great, but within within margin of error. And then the other one was much more within the margin of error. Again, the results empirically show that they had solved this macroscopic clock paradox with general relativity. And I believe they also use some elements of special relativity. Gravitational lensing. We've all seen them lately, especially from James Webb Telescope. The curvature of space-time acts a lot, bends light, much like in a telescope that Galileo used 500 years ago and that we're going to use from stellar view now, pretty soon. It acts like a lens. The effect is known as gravitational lensing and allows us to see galaxies that we could not see easily. And this was predicted by general relativity. But they said, forget it, Einstein. We got nothing we can test that with. It's not even testable. So, who knows if you're right. Well, it visually magnifies and brightens an object, okay? And Arthur Eddington in 1919 got a chance at a solar eclipse, total eclipse, went out there and was able to photograph using photographic plates and be able to see stars that normally we couldn't see during the daytime, and found that they had been gravitationally lensed. And the image of a distant object behind the gravitational field, let me just get into it, because I know we're running out of time. But here, if the object is behind the star, lensing can cause you to see two of them because light is scattered, and you'll see that. This is an actual picture of lensing. And the process, theoretically, we could see some of that, but at that time they hadn't seen it. Today it's much more common, but it was predicted. And here's Eddington's plates, and he's looking at these stars, and he was able to show, let's look at a positive, he was able to show that Einstein's work was correct. Now his predictions were correct. Eddington showed 1.61 arcsecond variance, and Einstein had predicted 1.7, and it was within error, but a guy named Dyson came along later and was able to show it better, confirming Einstein's predictions. In other words, until then, no one thought it happened, but he predicted that before we even knew about it. Then we went looking for it. And the way you look for it is go to a solar eclipse. And lo and behold, he's right. This made him an instant famous guy right there. All the newspapers carried it. So that's how that works. There's another test he passed.
One question from
Yes.
Atul. Why is light bent by the space-time curvature? Do photons have mass?
No, they don't. But remember, it is talking about curvature, and everything tries to travel in a straight line. If your straight line is curved, then you're going to follow that line. It's hard to imagine it in 2 dimensions, okay? But things will continue to travel in whatever straight line they have, and if it turns out it's curved, it will move along that path because there's a gradient there. Not a satisfactory answer, but it's all 3 dimensions of it are curved. So it will go around much like light can be bent by a lens. And if light is bent that way, strong gravitational masses that can cause a large amount of space-time curvature can cause light to bend that way. It's not about mass. It's about the fact that it's moving in that straight line, and space itself is curved, and it's going to follow that path. Okay. GPS. Geopositioning system, right? It's used, we use it, you use it, everybody uses it all the time. It allows us to find our location on Earth. And it was originally deployed in the 70s for the military's use. We use GPS. Russia has GLONASS. Europe has Galileo. Your phones can support usually GPS, Galileo, and GLONASS. Typically, you won't be able to use it, say, in China or India. It may not work. I don't think they support those. And they interact, they'll work on their own, or they'll interact with others. But it relies on receivers and satellites, quantum mechanics, and relativity. Sorry, I have to bring in quantum mechanics. But there are 24 satellites out there plus a few spares. They're about 12,500 miles up. And the devices, you need to connect to 4. 3 gets you your location, 4th gets you your altitude. Extremely accurate atomic clocks are required. All right. And the circuits have to take those equations for relativity into account, built in to the satellites. The distance from a satellite is measured by, well, the speed, which is c times time. And it looks for how long it takes for the signal to go back and forth. If the accuracy is within a millionth of a second, which is great, you'll be off by 1,000 feet. Not great. So GPS satellites have to work within nanoseconds, billionths of a second, have to be accurate and synchronized. So accurate distance is known if you have one satellite, right? You can bounce the signal back and forth and you're somewhere there based on the distance. But you need multiple signals, multiple satellites. And what that means is one satellite gets you part of the location, a second one now gets you closer to where you are, a third signal locks it in, the 4th one gives you the altitude. And usually your phone, your car, your handheld device can see at least 3 or 4 of these. If it can't, it won't be able to lock in cleanly. Like if you're driving underneath the, on the Bay Bridge sometimes. They need to account for relativity. Remember, GPS satellites are moving at 6,000 miles per hour. And they're 12,500 miles overhead. So time is affected by relative velocities and by gravity in the microgravity environment. So those 2 theories have to apply. And what happens is special relativity shows using the Lorentz transformation that relative velocity will be about, variance will be 7 microseconds per day, run slower. And then because of gravitational effects, you can take that into account with Lorentz transformation, and it'll be 45 microseconds a day, and it'll be faster. So you look at the difference, and what happens is it's 38 microseconds a day. Who cares? 38 millionths of a second? I don't care. Well, you should. Light travels at 1 foot per nanosecond. So 38 microseconds is 38,000 nanoseconds per day, which is 38,000 feet per day, which is 7.2 miles. Without taking relativity into account, our GPS systems would be off by 7 miles a day. So there's your watch if you have it, or your phone, or the GPS navigation system on your car. If it wasn't for relativity, we wouldn't be able to use them. We'd be off by 7 miles a day, cumulative over time, getting worse and worse. So everything is synchronized to atomic clocks. Relativity and quantum mechanics go hand in hand.
Okay, we have another question.
Yes.
This is returning to the planetary orbits. So the mass of the sun causes a distortion, a warping of the curvature of space-time. So does that mean that the mass of the planets doesn't really play a role in revolving around the sun?
It does. In fact, the orbit of Jupiter and the sun puts the center of rotation, even the sun goes, it's a little bit outside its center out of that. With Earth, it's insignificant. It's just that the masses are so different. But if the sun represents 99% of the mass, and roughly Jupiter is 1%, and everything else is that teeny bit within error, then they're about 100th of a mass apart. And so Jupiter's mass does play a role, and the sun does wobble when Jupiter is going around it. The sun isn't just sitting there perfectly just spinning. It's kind of doing its own little wobbling because of everything else in the solar system, especially Jupiter.
A center of mass, does that mean the barycenter?
The barycenter, correct.
Okay, thank you.
Okay. Okay, a neutron star, right? Now, a low mass star like a yellow dwarf star, which is our sun, it's a dwarf star. Sad. But in any case, well, I guess it would be dead if it was any bigger. It will eventually, in 5 billion years, die off and become a white dwarf. All nuclear fusion, hydrogen burning will end. It'll just glow white for 1 trillion years and turn into a cinder block. Larger mass stars can turn into a neutron star. Bigger ones can turn into black holes. So we're not here to talk about the astrophysics and stellar life cycles, but let's focus a little bit on this neutron star bit. So stellar core after a slightly bigger mass star than ours collapses into pure neutrons. It doesn't have enough mass. It has enough mass to collapse the electrons in every atom into the nucleus. Electron plus protons forms neutrons, and you've got a neutron star. But neutron degeneracy is still stronger than the mass's space-time curvature gravitational force to keep it just that size. Whereas a white dwarf, I'll have 80% of our sun's mass and be the size of Earth. A neutron star can be more than the mass of our sun, but it'll be about 12 miles across, the size of New York City or so. So it's extremely dense. They have a diameter of about 12 miles. Mass is that, and they spin very fast. So what happens now is you get something that's that dense, that hot, and that much gravitational field generated, and then you collide them, and you generate waves like ripples in space, like on a pond. And General Relativity predicted this. No one could test it until 100 years later. In other words, you're full of it, Einstein, even though all the other stuff is good. First detected in 2015. And by the way, here we are, and LIGO detected it, which is our gravitational wave detector telescope. And on August 17th of 2017, a spectacular collision occurred. By the way, August 17th is when we had the great solar eclipse also. Interesting. Anyways, 2 neutron stars collided, 1.6 and 1.1 solar mass. General Relativity predicted it, and here's the cool part. We have a gravitational wave detector, gravitational wave telescope. It's big in Louisiana and in Washington. Now, what it's doing is that it's this laser beam, it's allowing the light to be interfered enough so that they'll cancel each other out, the beams. But if a wave comes through, a gravitational wave, this can detect the change in length of less than a proton. It will throw it out of interference, and you'll be able to detect some light, which means a wave went through. Well, this detected it on that day. And what happens? In 130 million light years away in the Hydra system constellation, it triggered the detectors in both locations. So if one of them picked it up, not the other, maybe they had a little tremor, but both in the US picked it up. In fact, we had what's called, it was picked up by gamma ray bursts. It was picked up by what's known as, I thought I wrote it down, multi-messenger astronomy. And these stars were traveling at about 1/3 the speed of light. And basically, according to NASA, what happened is this: they're in a decaying gravity. And a bunch of things happen. So out of relativistic speeds, you end up with all of this matter going out there. LIGO and Virgo detected it within 12 hours. LIGO is in the US, 2 of them, and Virgo is in Italy. And in 12 hours later, because we knew where it came from, we're able to point our telescopes, including Hubble, at it, and we determined where it was. And this is what I mean by multi-messenger astronomy. You're looking at Hubble detecting it and the light over 6 days. You're looking at basically UV and optical. You're looking at here, gamma ray telescopes detected it. and also gravitational waves. Amazing. And it was first detected by gravitational wave detectors, and Einstein predicted it 100 years earlier. Now that's the way you pass a test. By the way, material was blown out in a normal state of matter, and the models predicted some heavy metals, which it did do. Spectral analysis confirmed that. Heavy metals like gold, silver, platinum, uranium were formed. And basically spectral analysis showed 50 Earth masses of silver were generated, 100 Earth masses of gold, and 500 Earth masses of platinum, and roughly a black hole was formed afterwards. Okay, so we're almost done. And this is powerful. I mean, think about it. GPS works, gravitational waves, gravitational lensing, all of these things. They throw every test at it. There's some Tom, Dick, and Harry right now saying Einstein was an idiot and I'm going to prove him wrong. Well, bring it on. You know, and I have yet to see the guys get messed up. So relativity is rock solid theory. All right, where do we go from here? There is controversy. It turns out relativity and quantum mechanics don't play well with each other. I'm not saying it's wrong, relativity, but there could be some changes. They do not play well together, and in order for us to achieve the grand unification theory, they need to play well. There's some concern about space-time, the mathematical model, you know, does it really exist, that type of thing, quantum foams and all that. Very interesting theoretical stuff. There's also different ways of looking at quantum mechanics and string theory, but string theory comes out of M theory, which is 11 dimensions in the 10 dimensions. And by the way, string theory is untestable as far as we know. So how accurate it is it? It's debatable, but it is a very promising theory still. So that's TBD. Issues with black hole singularities, like I said, anytime you have infinity, we don't know what's going on in there. We can talk about and act like we understand it, but at the end of the day, we don't know what's going on in the center of a black hole. That's going to take time to develop better theories. Relativity can't do it. It comes up with infinity. Quantum mechanics is weird because it comes up with infinities because we're trying to figure out quantum gravity. And so we're getting there. Maybe not in our lifetimes. So we'll see what happens. So, but it remains extremely successful. Do not doubt it. It's made our modern world very incredibly useful, the tools and technologies we have. But we'll see what happens in the long run. But that's what science is all about, right? Nobody said it's going to be permanent. If it changes, that's a good thing. By the way, we're out of time. I'm not going to talk about time travel, no matter what anyone says. Based on what we know now, the bottom line is, based on current theory, we cannot travel. We cannot time travel. Yes, everyone's got an idea, but I have yet to see someone prove it beyond some esoteric, you know, unless I get the flux capacitor or from Star Trek's, you know, Heisenberg compensators and other things, we won't be able to do it. But, you know, it's interesting. Well, that's it. And gosh, you know, I've got to thank the dogs who've been listening to me, especially Tristan and Rhonda. And thank you very much. I hope you guys found that interesting. Oh, good. We still have about 25 people, so we've held on to everybody. And is there any question? I will stop sharing.